So for today's lesson, we're going to revisit the concept of modeling. And we've talked about, power function regression and exponential regression. Today we're going to talk about logistic growth and logarithmic regression. We're going to add that to our list of things. And we're also going to talk about how we can use the Scatterplot and certain tests to determine which one is the best fit. So a lot of calculator work today. Make sure you have a working TI-84 calculator. All right. If I could just have a working thing. There we go. So for today, we have to remind ourselves what the graphs of these functions look like in exponential growth. This is the general shape of it. So what we're going to do today in exponential decay, and then remember the logarithmic functions are the inverses of exponentials. So logarithmic growth that has a base greater than 1 is the inverse, remember, to the exponential base greater than 1, and same with the base between 0 and 1 for the logarithmic and exponential. So what we're going to do today is we're going to look at scatterplots first to determine if something is a good fit, and then we're going to talk about how we can use our list 1, list 2, list 3, list 4 to determine which function model is the best. And we're going to also introduce you to a new function today. Yay. Rapid growth or rapid decay suggests exponential models. However, if it starts off growing rapidly and then kind of dies off over time, that's suggesting to us that there's a logarithmic model in there. So we have to keep that in mind when we're looking at the scatter plots. So for this question, it's the GDP for various years throughout history, and then make sure for this particular model we're going to set up X representing years since 1950. So this is year 0, this is 10 years later, 20, 30, 40, and 50. So in list 1, I would like you to enter this data. And in list 2, I would like you to enter that data. And then you're going to probably make sure y equals is empty, but you're probably going to just do zoom stat. And go ahead and pause the video to get your data entered and to look at the scatter plot. So now that you've entered your data and looked at your scatter plot, you're going to see something that kind of looks like this. And that is indicative for us of an exponential growth model. We might determine, through other testing that something's a little better, but, I'm thinking exponential regression is the way to go here. So if we use our exponential regression modeling, remember that was on our calculator. So once you have your data into list 1 and list 2, you go to the calc menu and you choose exponential regression, if that's what you were thinking. And then you go through the process of telling it it's in list 1 and list 2. Kind of skipping this step because this is old. And they want to know what is the growth rate. So for the way the formula is set up, A is the initial value for the function, B is the growth rate that's holding up the exponent. So if I look at the growth rate of, like roughly 1.035, that is, remember the base is 1 plus the rate. So if you take 1 away from that, we get roughly 3.5% of a growth rate. And the correlation coefficient is 0.999. So our guess of it being exponential regression was a pretty good one. Go us. All right. Now if we typed our function or stored our function into y1 and we graphed it against the scatter plot, that is a real nice fit. So I'm going to kind of steal the data off my calculator that I've already gone through the regression. And it was roughly 1812.01 for my a value. And then approximately 1.035 for my base, raised to the x power. So then they want us to estimate the gross domestic, I forgot what that stands for, GDP, for the year 2020. So remember this, it was measuring years since 1950. So 1950 to 2020, that was 70 years later. So go ahead and plug in 70 or use your table. It doesn't matter how you plug it in, but someone has to plug in 70 for x. We're going to get approximately 20136.55. So if you were just kind of watching the magic happen, I don't know what the label is on there, I would suggest you pause the video and you make sure you go back and you remember how to enter data into list 1 and list 2, because we're about to get real crazy with the calculators. So go back and redo that question if you were just watching me do it, because clearly I didn't do it. I already did this problem a long time ago and I just copied my answers. Alright, so now let's talk about something that's a little new. We can talk about logistic growth today. So logarithmic growth is unrestricted, and it increases at an ever-increasing rate with no upper bound, which doesn't really apply to like real life. The amount of growth is limited by factors within, the parameters of the problem, like population or space. Like there's only so much that like a population can grow until we run out of space or food, water. So we would create a function that would show initial growth, but then it's going to slow down and basically level out and approach somewhat of a horizontal asymptote, which would make sense if you think about like, a very crowded city. At some point, there's just no space and you're not going to be able to grow anymore. So the logistic growth formula is provided to you here. The t is any real number for time, and then a, b, and c are going to be positive constants, and then c is going to be the limit to growth. So the good news is I'm not going to make you do tons of work with this. I just want you to be aware that there is a logistic growth formula, and I want you to understand why it occurs. And this is the formula that would be used in more of our applied sciences and social sciences when they talk about population growth. And if we predict, like, okay, right now McChesney Park is seeing an increasing rate of people who are moving in, but at some point it's going to have to flatten out to a carrying capacity, which is the horizontal asymptote. So fun times. All right, so this next question, they want us to make a scatter plot. So you're going to type your data into list 1 for X and list 2 for Y. So please pause the video and get all that data typed in. And then, I think this time I'm going to pause my video too, and I'm going to get it typed in. So you pause too. All right, we're back. So I have my data entered into list 1 and list 2, and they want me to make a scatter plot. So first thing I'm going to do is make sure my y equals is cleared out, and then I'm going to go to zoom stat. It's the easiest way to get a good window for your scatter plots. Except my scatter plots aren't turned on because I never did a problem yet today. So let me turn those on for list 1 and list 2. And now I'm going to zoom 9. And that's the function that I'm seeing when it's graphed as a scatter plot. So go ahead and jot that down on your paper. And then it wants us to determine the logistic function to the model. So, yay. What we're going to do is that logistic model that I gave you, we're going to plug in the information. On your calculator, sorry. Go to Stat, Calc. Logistic. All right, there we go. So remember our data is in list 1 and list 2. I don't have any frequency lists because I didn't have any recurring values. And you know what? Let's go ahead and store the equation into y1 because once this comes up, I do not want to type it. Varies, y varies, function, first one, sounds good. And let's calculate. So what they're going to do now is they're going to give you a screen with, one more time, with a lot of information on it. So it tells you what formula the logistic model is in, C divided by, and then that whole quantity, which is the same formula that matches our notes. And now they give you constants for A, B, and C that you're going to have to basically put onto your paper. So on your paper for the logistic model, get back to my screen. Here we go. So the logistic function is y equals, I forgot exactly what it said on the calc, but I wrote down 10.002 for the C value, divided by 1 plus, and then we had what, 2.357. I have a really large denominator, so I should have made that a little bigger. And then times e to the, and that was the A value, by the way, and then e to the negative, that's part of the formula, 0.501, and then t remains a variable. So this is the model itself, and the good news is you're not going to have to type that because remember we stored it into y1, so go us. Go back to your calculator, and remember it got stored into y equals, so there he is. And if you go ahead and hit graph, you're going to see your logistic model go pretty closely through the scatter plot. I didn't pay attention to anything else on the screen on the last. Let me go back. Enter. Enter. They don't give any correlation coefficients here because of the parameters of the logistic growth model. So we just have to kind of look at the shape of the scatter plot versus what was graphed and say, like, yeah, it was a good fit. But remember, we're supposed to predict a value for when x equals 20. So you can either go to the table or you can hit trace. And then you need to make sure that you're actually on the curve, which now we're on the curve, and then type a 20. But I'm not in the right domain. My window was for the scatter plot, and it cut off the window at 7.7. So I need to make the x maximum go larger. I have to go to like 25. I don't know if the y has to go larger or not. I guess we'll just live dangerously and try it. I think we'll be good. So now I'm going to trace, make sure that I'm on the curve instead of the scatter plot, and type a 20. Boom. All right, there we go. Now, this makes a lot of sense because our logistic model is going to reach that carrying capacity at roughly 10. Basically, it looks like a horizontal asymptote, so it doesn't surprise me when the value comes out to 10.000 something. All right, so I don't know if that fascinated you as much as it fascinated me. Probably would have been more exciting if I cared more about mice and their population. That's what that question was about. So make a conjecture about why the logistic model may fit the data. So as far as the shape of the graph goes, it does increase rapidly, and then it kind of flattens out to a horizontal asymptote at a certain point, so it reaches that carrying capacity. And, you know, nature has a capacity that it can't really exceed unless you give it more space or more materials to work with. So there's only so many mice that can live in an area, and at some point there's going to be other effects to the environment. So that's why it flattens out. So we can use our calculator to find linear, quadratic, exponential, logarithmic, or logistic regression on a set of data. So it's up to us to determine which one is the best fit. So today we're going to talk about how we can use our lists to determine which one is the best fit through testing. It is the most efficient way to determine it. The good news is I'm not actually going to make you do that on an exam that I give you in class, but I just want to introduce you to how we could do it, and we will practice it with our homework. So this next screen shows you a bunch of ideas. We have seen linear regression, we've seen quadratic regression, power regression, exponential regression, logarithmic regression, and I like this screen because it has the same scatter plot with all the different regressions kind of going along with it, and it's pretty easy to see like which ones look the best, frankly. So like in this domain, like obviously it's not linear or quadratic, power doesn't really fit nicely either, not logarithmic. But logistic and exponential regression look real nice for that scatter plot, so we'd have to determine which one we like the best. Over the domain that is displayed, for that particular one, exponential and logistic were the most accurate. The exponential model has the strongest correlation coefficient out of the other ones. Remember, the logistic growth one will not give you a correlation coefficient, so you just have to kind of go along with the shape. We didn't, because of the domain that was showed, we didn't really see that carrying capacity issue of it reaching a horizontal asymptote. So we'd have to kind of consider if we liked the domain that we were looking at. If we were to look into the future, we might change our mind. All right, so to linearize data models. So data models that are clearly not linear, and we have to determine whether they are quadratic, exponential, logarithmic, or power. Notice logistic is not in that list, so we're not going to worry about logistic growth. Don't confuse logistic with logarithmic, because, you know, I do, because that's the kind of person I am. These are the tests that we're going to be able to do. So if you want to determine if something is quadratic, then you would be able to determine if x and the square root of y ended up being linear. If you start thinking about the math associated with that comparison, it kind of makes sense, because if you compare the x values of a quadratic to the square root of the output, they should have like a direct linear relationship. You know, squaring a 3 gives you a 9. If you square a 9, you get a 3. So, you know, they have that nice relationship to each other. Similarly with exponential, they have a nice relationship with each other if you graph x comma natural log of y. Logarithmic is natural log of x comma y. And then the power functions would be natural log of x and natural log of y. So the good news is, at no point do I expect you to memorize these little test comparisons. We're going to be using list 1, list 2, list 3, list 4 in our calculators, and list 5, sorry, and list 5. And we're going to keep them the same all day today. So we're just going to kind of jot down what we're doing in each list, and then we're going to keep doing it the same way because I'm going to confuse myself today. All right, so in our list, and you want to jot this down somewhere in your notes, in list 1, we're going to have our x values. In list 2, we're going to have our y values, like we always have. But in list 3, we're going to be calculating the natural log of list 1. And then in list 4, if we need it, we're going to be calculating the natural log of list 2. And then in list 5, we're going to be calculating the square root of list 2. Notice I didn't say like x for list 1 and y for list 2, which is what that is what it is. This is just helping me to know what I have to physically type into my calculator's list headers. So keep this handy. We're going to have to keep going back to this over and over again. Yay! All right, so when we do these various tests, these are the ones that we're going to be checking out to see if the power function, quadratic, exponential, or logarithmic functions are going to be the best fit. The only other option that we would have is we would have to go through and do all the regression tests and then like jot down what their correlation coefficients were and determine which one is the best and look at their scatter plots. So believe it or not, what we're about to do is the faster method. It's the more efficient method. But I think I already told you wonderful news. I'm not going to make you do this on an exam, so calm down. I will make you find the regression, but I will tell you which one to use. Little side note here, there's no test for logistic data. So, and there's no correlation coefficient either. So if you think it's logistic, that's because it'll be looking like it's approaching a horizontal asymptote. And that's really easy to see when you look at the scatter plot. You just have to be careful about your working domain. Like, do I care, what happens way, way, way out there? Because maybe I only want to look at from 0 to 5. It depends on your problem. So this particular question here, we're going to pause the video and we're all going to type in our data into list 1 and list 2. So put the number of days in list 1 and the machines in list 2. All right, so we're back and we have our data into list 1 and list 2. And then it says, please make a scatter plot. And then let's kind of, because of the way the graph is going to look, let's make a prediction what we think is going to work. So make sure your y equals is cleared out and then zoom stat that baby. So the shape is suggesting logarithmic. It's doesn't have that obvious horizontal asymptote to even worry about logistic, and it's clearly not exponential because it doesn't have that like go backwards that swoop up. We might determine something different, but I'm thinking logarithmic. Hope you agree. But here's how we're going to figure it out. What we're going to do is we're going to test for logarithmic, which if I go back a screen, actually I think it's right here. I wrote it down in the next part of the notes. So create a graph for the logarithmic test, which is the natural log of x and y. So in list 3, remember we're going to set up the natural log of list 1. And then we're going to compare some stuff. Ready? So back to my calculator. I already have list 1 and 2 in. So now go over to list 3. And then in the header of list 3, tell it to apply the natural log to all of your x's, which remember those were in list 1. And so there's the data. It did the natural log of each of those x values. And now what we're going to do is we're going to look at a scatter plot that compares those two values. You have to go in the correct order though. Remember it was the natural log of x, the natural log of y. So going to our scatter plot setup, which if you don't mind, I think what I'm going to do is I'm just going to turn this first one off. And then I'm going to go up to list 2, or scatter plot 2. I'm going to turn this one on. And instead of list 1, list 2, like we normally do, we're going to be doing list 3, list 2. Okay. So now when I zoom stat that, wow, that is really stinking linear. So that tells me that our assumption that it was logarithmic is a good one. Because when I compare the natural log of the x's to the y values of the original data, that's the test for logarithmic growth, and because it produces a very linear looking scatter plot, I'm going to say yes, that was a good one. So now we are going to choose the linear regression. This is where it gets kind of confusing. What we just did was just to see if linear regression was logarithmic regression was a good one. Now we're going to go ahead and compute it. So we're going to calculate logarithmic regression. So go find that one. Not logistic, but right here. It's the, they write natural logarithm, I think just because it's shorter. I don't know. Or maybe that way people don't confuse it with logistic. I don't know. Either way, logarithmic regression. Remember, our actual data is in list 1 and list 2. So you want to keep it that way. And this time I will be storing my equation into y1. And then let's do this. So it's going to give you the general formula for a logarithmic regression equation. It's going to give you the values for a and b, and look at that correlation coefficient, 0.999999. So that was like super good fit. We're going to write down our equation though. So on our paper, please write down, they already have the y equals blank. Now they do kind of put the formula backwards. See how they put the a plus first? So usually we put the logarithm first. So we're going to put 217.4, that's fine, natural log of x, and then plus the a value of, well, I crossed off half of it, 614.4. So we're rounding to the nearest tenths place simply because I'm too lazy to write any more than that. And then it says on day 9, there's 200, there are, and they want you to plug in, oh, you know what? Actually, the notes, they rounded to there's a whole number, so we're even better keeping the 0.4 on the end there. But when you plug in a 20, right, or sorry, a 9 right there, and whether that be in your home screen of your calculator, on your table, whatever, you get approximately, and we should round to the nearest whole number, 1091 infected machines. Morbid. All right. All right. That was really, I mean, testing for which type of regression is best is kind of tedious, but if you're not real sure, like I always start by looking at the scatter plot, and then I can kind of tell. And if I'm like tinkering between like, oh, I don't know if it's exponential, or I don't know what else I would confuse with exponential, but if I wasn't sure, I would do my test and I'd see which one worked out better. So this next one, we have the brightness of a point of light measured at different distances. So in your calculator, and I'm looking at the next one, it says under the word practice in your notes. So enter this data, distance into list 1 and brightness into list 2. I'm going to pause the video, and I'd like you to do the same. So all I've done so far is entered the data into list 1 and list 2. That current list 3 is still the data from my old problem. So if I want to use list 3, which is the natural log of x, I need to like resubmit that into the header and have it recalculate everything. So for now, I'm going to leave it alone. You could clear it out if you want. It's not like we're going to be using the old data. That'd be goofy. But I do want to look at the scatter plot. So I want to turn back on that first scatter plot, and I want to turn off the second scatter plot. Remember the second one that we had turned on was the test for the logarithmic growth. I don't want that one on right now. So let's zoom 9 the original data and get a picture. Oh, that's lovely. I don't know about you, but I'm feeling exponential decay. So what we're going to do is we are going to test the exponential decay test, which if I look back at my cheat sheet, it said we should be doing exponential function would be making list 4 be the natural log of list 2, the y's, and then we're going to plot list 1 versus list 4. So, edit. I'm most definitely going to clear out list 3. I have no interest in having the old data, much less. I actually don't need to use list 3 at all. Just to keep things consistent for list 4, I'm going to go ahead and keep what I said for the original header. So list 4 for us is always going to be the natural log of list 2, the natural log of the y's. So natural log of list 2, and then hit enter, and it will calculate all of those natural logs of the y's. And now we're going to be plotting natural log, it goes list, I was confused these, it goes list 1 versus list 4. So, if you don't mind, I'm just going to change this guy. List 1 versus list 4. I'm sick of turning them on and off. It gets very tedious on this emulator because it's kind of slow. You should zoom 9 again to reorganize the data. And you know what? I mean, it's kind of linear, but it's not really linear. So maybe we should try something else. Another shape that kind of, swoops down, whoops, wrong way, down like that. Maybe it could be a power function. Like, there's many different types of power functions, so maybe this is one of them. So the test for a power function is natural, I get this one confused too. It is the natural log of list 1 and the natural log of list 2. So natural log of x, natural log of y plotted against each other. So back to my stat. Oops, edit. I'm going to go to list 3, which is where I'm going to store my natural log of my x's. So natural log of list 1. And then in my scatter plot, I'm going to look at list 3 versus list 4. That would be the test for power function. So list 3 versus list 4. And then zoom 9 again to recalculate that window. Oh, that's nice. That's nice and linear. So it turns out this is a nice power function. So I'm going to go ahead and go through the fun of finding my power function through regression. And you have to scroll around until you find the right one. So there's power, A. Now make sure when you enter your data, remember your actual data is in list 1 and list 2, the x and y. There's no frequency list here, and I'm going to go ahead and store it into y1. I wish they'd make a shortcut key for y1. It would make me very happy. Alright. Oh, that's good. Now it does have a negative correlation coefficient, but that's just because of the negative slope. But negative 0.9999, that is a good fit. Alright, so writing our power function down. Y equals, the A value is 7316.1-ish. Let's say 11, might as well. And then times x to the negative 1.999 power. Lovely. All right, so then the follow-up question says, estimate the brightness at 100 meters. So when x equals 100, you either need to manually plug that in or use your table or something. You're going to find about 0.735 candelas. That's the label for how much light's going on there. That's a fun one. All right, so, man, great news, guys. I'm never going to make you figure out which one is the appropriate one through testing on an exam for me. So I just want you to be aware that there are ways we can test it out. But beyond homework and working together through examples, we're not going to have to do that. And that last example was a perfect one where I kind of thought it was exponential decay, and then I went to go test it and realized, actually there was a much better one. So some kids will say, Abruzzo, I could have just done power regression and exponential regression, like one right after another, and determine who had the better correlation coefficient. And yeah, that is true. That is another way to come up with that, okay? So, but great news of the day, you're not going to have to do either one of those things. When it comes to a summative for me, I'm going to tell you, use logarithmic regression or use exponential regression to determine this, and then you, just like we've always done with regression, take your regression equation and plug in a value and find out the prediction. All right, hope you enjoyed that. That was a good time.